Data Types Part 2 of 2. In this nugget, we conclude our discussion of the core primary data types in Python. What you're about to learn, among other things, is that all three of these data types, tuples, lists, and dictionaries, are related to each other and quite similar in terms of they allow us to pack more information into a single variable. There's a lot more we can do with them. We need to understand the ground rules and then begin to apply them in a practical context. Let's get to work. First, let's look at tuples. The first thing you might be wondering, actually, as you start to work with these bad boys is, do I sound like a jerk when I pronounce tuple? That is to say, a common question among programmers, in particular Python programmers, is there an official way to pronounce this? Is it tuple? Is it tuple? Bottom line is, really, there's no official way to pronounce this. You can go either way. From what I understand, Guido van Rossum does pronounce it tuple, but there's just as many Python programmers, myself included, who tend to pronounce it tuple. Regardless of pronunciation, let's jump down to the third bullet point and define what a tuple is. A tuple in Python is an ordered set of data. This is a very generic definition because actually tuples exist outside of Python. In fact, my first introduction to this word was the second official general definition, where in relational database theory, a tuple or a tuple is a single row in a database table. However, in Python, a tuple is an example of a sequence. You'll remember in the previous nugget where we introduced strings, we mentioned that a string is an indexed sequence of characters. Well, tuples are the same thing. They're a sequence in terms of each element in the tuple is indexed, and therefore order is significant. We're also going to see that lists are our third sequence type. Dictionaries are actually not a sequence. More on that later. Now, I know we haven't gotten to lists yet, but we're certainly going to be doing a fair amount of comparison and contrast between tuples and lists because they look a lot alike, at least at first. They're ordered sequences of data. The big difference, the main difference between lists and tuples is that a tuple is an immutable list. In order to modify a tuple, you're essentially going to need to create a new object. Lists, as we're going to learn shortly, are really the true workhorse data type when we want to pack more than one element into a variable. So the question comes to mind, well, what good are tuples? Tuples in your Python programs are awfully useful for smaller data sets, and also, due to their read-only nature, they're good for any data that you want to protect against overwriting during program execution. It's good for storing static program data, constants in other words, constant data. As far as the syntax for tuples is concerned, let's take a look down at the bottom of the screen where we're defining a name called a tuple, and the thing that will let you know right off the bat that we're dealing with a tuple and not a list is that tuples use parentheses. We're actually going to see that tuples use parentheses as their delimiter, as their opening and closing mark. Lists use the square bracket, and dictionaries use the brace. I'm not going to call them squiggly brackets because that's not precise. Now, within that tuple, you'll see a comma-separated list of types of elements. This example gives us string, 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 float, and integer. So what I want you to see in this example is that tuples are nice because we can pack more than one data type in that object. I've heard tuples described in practice by professional Python programmers as sealed packets of information. Any constant data that you'll want to refer to maybe once or several times in your Python program and you want to prevent that data from changing, well, that's a good application of when to use the tuple data type. Now, what can we do with tuples? They're read-only, which means we cannot append to them. Append in our context is a fancy word for inserting a new element in that object. We can't do that. Basically, you can just retrieve the entire tuple, or we can, as we've learned in the previous nugget, slice tuples. Now, you'll notice here again we have the same zero-based index where we're working from left to right, although instead of whereas in a string, each character in that string is individually indexed. In tuples and lists, each object in that tuple or list is indexed, you see? So in this example, we have CBT, nuggets is obviously string data type, and then 1.0, which is a float. We can use our slicing syntax to bring out one or more of these elements, starting with 0 if we're moving from left to right, and then if we're moving in the reverse direction, the rightmost element is at the -1 position and then goes out. So in this example, our first example, if we run a tuple and then 1 to 3, then this is going to come back first with nuggets, and then it's going to return is. But you'll remember that when we use slicing, the second value after the colon is not included in that slice. So in this case, we would just return nuggets is. Likewise, if we look at the second example, a tup, -4 to -2, this is going to return CBT and nuggets, but it will come up to but not include the second value in the slicing set. Before I demonstrate tuples, let's look at one more whiteboard slide here that gives us additional information. The first thing, yet again, to remember above all else is that tuples are read-only sequences, so therefore we cannot modify elements in that tuple. We're going to learn when we look at lists very shortly that we can modify lists all day long. We can use methods like append, extend, insert, remove, and pop to add, insert, remove, just basically what you're seeing here with these descriptive method names, elements in the list. But tuples or tuples are sealed packets of information that are essentially constant data. What we can do is run, say, the len built-in function, which you'll remember from the previous nugget. If we pass in a tuple, will give us the length of that tuple in terms of the number of elements within it. We can also perform type conversion. Remember in the previous nugget where we looked at the string and the integer and the float type conversion functions, here we have list and tuple. Tuples are read-only. Although we can't change them, we can search within a tuple. There's a count method that we're going to look at, and we can also test to see whether a particular value or string exists in a tuple using in. To summarize, why would we use tuples? Tuples are considered by most Python programmers to be faster than lists, primarily because they're immutable objects. Tuples are used in practice for write protection purposes. And finally, tuples, but not lists, can be integrated with dictionaries, which we're going to look at after we look at lists. Before we get started with looking at tuples in practice, as you see here, I've opened up the Python shell. I'm going to give you a really neat workaround to a problem that many Python programmers, myself included, find annoying with the idle environment, and that is there's not a clear screen functionality built in. So you can wind up with quite a bit of clutter on your screen and just want to, like I do oftentimes, want to start with a blank slate. Now you notice that we do have in the shell menu a restart shell option. That essentially blanks out your shell, cuts off everything what you've been doing previously. And that can be helpful to, say, reduce the memory footprint of idle when you're working in interactive mode like we are. The best workaround I've seen to clearing the screen takes a couple lines of code. You actually have to write a function to do this. And remember, a function is a modular unit of code that performs some work that exists outside or just as a part of your Python program. I'd normally call mine wiper, but you can call yours whatever you want. When you define a function, you use the def keyword, space, and then provide the function name. And then if you're not going to involve any input parameters or arguments, you would just do open and close paren and colon. When you hit enter, you'll find that Python automatically indents 4 spaces by default. The first line, when you see some statement that involves compound action, like a function declaration, the first line that includes the colon is what's called the header. And then once we indent and start working, the rest of the body of this function is formally called a suite. I'm getting ahead of myself a little bit because we're going to talk about functions in great detail later in the course, but we might as well look at it now. All I'm going to have this wiper function do is run the print function. And I'm going to have it print 100 new line characters. Now again, we haven't talked about escape sequences yet. The \n is an escape sequence that results essentially in simulating a press of the return or enter key. We'll be talking about those in great detail in the next module. But for now, I'm going to close this out now by hitting enter and then enter again. That creates this function. Now because we're in the interactive environment, this function is going to exist only in memory as long as we have the shell open. So it's of limited use. You'll basically, each time you start the shell, you'll need to create this simple 2-line function. But what's cool about it is that you can then call the function, in this case case wiper with no input parameters, and it gives us enough new lines to give us a clean screen. That's all. Let's begin by creating a sample tuple. I'm going to call this new tup. And remember, tuples use the parentheses. I open and close them by default to make sure I'm not forgetting anything, and I'm just going to add a few elements here. If I run the type statement, the interpreter tells us, sure enough, we've created a tuple. And as you see, we have 1, 2, 3 elements. We can check that length, of course, by running the len built-in function and passing in the name of our object, 3, sure enough. And we can actually verify the type of individual elements within that tuple by running type, but inside the type function, we would include the name of the tuple and then the index position, 0, 1, or 2 in this case, of the element that we want to look up. So type, passing in new tup sub 2, is focusing on this guy right here. Now I'm going to come up, select the line, press enter to get it back, and then we'll verify that the string is for the position 1 element. We'll do it one more time and verify that integer is the first one. Good and good. We can work with slicing. I'm actually going to create a new object here called ntup2, and what we'll do is bring in new tup, and why don't we slice out position 0 to position 2. Of course, I have to spell the name correctly. There we go. So I've extracted 1 in some text, attached that object to a new name called ntup, but of course new tup still exists. Remember, tuples are immutable sequences. As far as methods are concerned, we need to remember that of course tuples are immutable, so we're not going to be able to do something like this. I'll call a new name tup_app, and we'll take new tup dot in order to access any methods that are associated with that object. And we're going to see that the method list is very sparse indeed for tuples. It's essentially only count and index. Just for grins, I'm going to use append. This is what we use and what I'm going to show you very shortly, how we can add new items to a list. And I'm going to see if I can add a string to the end of my tuple. Nope, we're not allowed to do that. What we can do with tuples, though, is query the list. So let's bring up the method list again in idle by using the name dot and then waiting for the method list to come up. We have count and index. Let's look at index first. I'm using my arrow keys to move up and down the method list, and then you can hit tab to complete. When we open up the parentheses, the help tells us here that this is going to return the first index value of whatever we pass in. I'm going to look for the index value of some text, and it tells us, as we know, 0, 1. Some text is in position 1. Now let's try this. What if we try searching for some text with capital S? That's not going to happen. This item is not in the tuple. Remember, case matters here. Whenever we're dealing with string data, we're dealing with Unicode, and Unicode has a glyph or an ID assignment to every character, uppercase and lowercase, as does ASCII actually. Finally, let's do a new tup count, and what count does is give you the number of occurrences of a value. Now, this isn't so exciting here because we have only one occurrence of each of those values. So if I pass in my pi here, it tells us we have 1. But let me create multi-tup, and then, as you see here, we have more than one occurrence of Tim. And if we pass that string in as a parameter, we now have 2 occurrences. Man, I've mentioned lists so much in our previous discussion of tuples, you probably feel that you halfway know them by now. And I hope that's true. At any rate, let's formally define the list. The list is defined by most Python programmers as a true workhorse data type. Because again, we can pack a lot of data into a single name, and not only that, because lists are mutable sequences, we can make edits or changes in place to a list all day long. They're extremely flexible. As you see in this example, a list, lists are denoted by the square brackets, but other than that, the basic construction of a list matches that of a tuple. We just have a comma-separated list of multi-type objects. In this example, sales, 25, admin, and 1.0. Same rules apply as far as slicing goes. We can grab 1, 2, or all of these objects using our slicing syntax, using our index and position operators. And what's even more cool here are the many methods supported by the list sequence. Let's take a look at some of these. These come to us courtesy of Dytel.com. These folks are really great programming instructors. Now, we can append to a list, and that's going to insert one or more items at the end of the list. So if we run append and then pass in spam, we're going to see sales 25 admin 1 comma spam. Count returns the number of occurrences of an item in the list. That works exactly like the count method in tuples. Extend is cool because you can actually embed lists, and I'll show you that in the demo in just a minute. Index returns the index of the first occurrence of a particular item. If an element is not in a list, though, a value error exception is raised. Insert will allow you to arbitrarily, whereas append, you insert your item at the end of the list only. Insert is cool because you can actually specifically note where in that sequence you want your new item to go. Pop and remove are both used for removing items or elements from a list. Pop will remove and return the last element in the list. Therefore, append and pop are bookend methods. You can also use it with an optional parameter to remove a specific element as well. Remove removes the first occurrence of an item from the list. Reverse will allow you to completely flip-flop 180 degrees the sequence of your list. And then this is especially cool, especially if you're doing a lot of inserts and appends. You can run sort to run a ascending or descending sort on the items in that list. Really cool. Let's dig in and show you how this stuff works. All right, here we are back in the Python interpreter. As you see, I've created a name called foo that includes, let's see, 1, 2, 3, 4 elements in this list, or 4 items. You see we have spam, 335, eggs, and a decimal. Couple points, just one initially that I want to make. You'll often see in programming literature references to variables named foo or bar. The expression foobar has a colorful etymology that I'll leave you on your own to figure out. However, in Python, you'll often find that instead of foo or bar, you'll find spam and eggs. Yet again, this is a tongue-in-cheek reference to Monty Python and their famous 1970 TV skit in which the guys were in a restaurant and pretty much everything on the menu involved spam. By the way, when you substitute some arbitrary name for a variable like foo or bar, or in this case spam or eggs, that's called a metasyntactic variable. Now here we're not using spam or eggs as variables, we're using foo, but that's the formal name for when you do that, and that's mainly for documentation or instructional purposes. Good and good. Let's create that object and then run type on it just to make sure all of our bases are covered. If we wanted to create a new name, I'll call it foo2. We can slice in just like we are used to. I'll just slice from 1, 0 to 3, let's say. That gives us spam, 335, and eggs. Well, what if we wanted to get rid of the 335 and we only wanted foo2 to be spam and eggs? That's easily accomplished. I'll create a new name called foo3. Now you note that I don't have to do that actually. I can just say, because remember lists are eminently mutable, I'll just redefine foo2. So to remove 35 from this list, easily accomplished, we'll do foo2 dot, and then when the method list pops up, note that we have a lot more we can do method-wise with lists than we could with tuples. I'm going to arrow down to remove, hit tab, and let's simply remove the 335 element. Good, so now we just have spam and eggs. What if we wanted to convert foo2 into a read-only tuple? Well, that's easily accomplished, isn't it? I'll create a new name called footup, or footup. We want to be careful with our variable names, and speaking of which, we're going to discuss the rules and best practices for naming variables in the next nugget. And we're going to do a tuple and pass in foo2. Foo2 now is still the list. If we do footup, we see with the parentheses that it should be a tuple, but we can verify that by passing in footup into type, and sure enough it is. Let's work some more with methods here. Let's bring back foo2, spam, and eggs. Well, let's extend this a little bit, shall we? So why don't we foo2.append, and let's add in our favorite pi character. See, if we want to get a count of elements, we can do a foo2.count. Of course, the count function requires an argument. You might think that count would give you a return of the number of elements in that list, but remember that's reserved for the len function. So let's select that line, hit enter to bring it back, and let's bring in the first occurrence, or the number of occurrences, of eggs. Of course, that's 1. If we add in eggs to the end of the list, of course, that'll increment the count. How about inserting an item into the list? Arrow down to insert, hit tab. Let's insert foo in position 1. There you go. Next, just for grins, let's insert bar in position 3. Next, let's run foo.reverse. That completely changed up the order. Let's do a foo.sort. Aha, we got a trace back. And I hope that the type error makes sense. Unorderable types, string to float. So Python got confused trying to figure out how to combine two different data types. Various ways around this, actually. One way that immediately comes to mind right now is that we can run the string function on foo position 0, which converts the 323.234 to a string. We can also do the same thing and bring in the 335 in position 2. Therefore, if we try our foo sort, and yet again we get a traceback. I did this intentionally to show you again a common mistake that newcomers to Python make when we're working in an interactive environment. Remember that unless we're making changes directly to a source name, that you're not doing anything other than simply sending an expression to the interpreter and then getting back the result. That is to say, these two string conversions were just fine, but because we have not applied them to the source object foo, you'll note that the sort function comes back with an error, and if we echo back foo, you'll notice that the first and third element in this list are still float and int respectively. All right, so to cut to the chase, let me just go ahead and create a new list really quickly and show you that they're sorted. The third and final data type we're going to look at in this nugget is the dictionary. And whereas strings, lists, and tuples are all sequences because they consist of an ordered index sequence of objects or items, dictionaries are mutable, but it's an unordered set of not individual items, but what are called key-value pairs. Technical synonyms for dictionaries are associative arrays and hash tables. Those are some $5 ways to refer to a dictionary. Now, the thing about dictionaries that's cool and why some Python programmers like to use them is because they're fast. They're fast as far as lookup, chiefly because each value is associated with a key, and each key is run through a hash function. A hash is where you take source input and run it through some mathematical algorithm to come up with a fixed result, fixed length result. And if we use the hashes in our dictionary operation, that's happening under the hood by the Python interpreter, of course. We're working with the plain text key values in our code. Working with the hashes involves much faster operations than the unhashed. Let's look at the syntax of dictionary objects. We have a name called adict that I've created, and we see the braces being the terminal characters in a dictionary, and you see key value pairs given. This example shows a mapping between English words for numbers and their Spanish counterparts. Of course, you can create any relation here between your keys and your values. There should be a colon in between 3 and tray. You'll remember that I mentioned, although I haven't yet demonstrated, that lists can be encapsulated inside of other lists. You can bring in tuples as keys as long as all elements in the tuple are either numbers or strings. In other words, they're immutable themselves. However, because lists are so dynamic, we cannot use lists as a key, because what happens again is that each key value you have is run through this hashing algorithm and it comes back with some fixed length result. If you included a list in your dictionary key, and you appended to the list, you removed an item from the list, that would force a recomputation of that hashing function and that hashing value, that digest, and it would break the dictionary. So therefore, lists cannot be used in dictionaries. Dictionaries are, I like to describe them as mini databases or mini lookup tables. They are mutable, like I said, so you can change these values all day long, but because of their speed and retrieval and the fact that you have this one-to-one relationship between a key and a value, they can be awfully helpful for introducing static or even in some cases dynamic data in your code. For instance, you might have a language education or language translating application, and this adict object would be useful because it's mapping the English word to its associated Spanish word. Dictionaries do have a handful of useful methods. There are more than what you see on this whiteboard. I'm just giving you the major ones. As far as retrieving data out of a dictionary variable, you can call on keys and values specifically, or you can run the items method to bring back key value pairs. I told you about the pop method when we did lists. You can use this to remove key value pairs from a dictionary. Clear will actually purge all items from a dictionary. To start, you'll see I created a name called months, and I've opened this up with the brace character. Please don't get confused between the parentheses and the brace. Dictionaries must use the brace as their terminating characters, and as you see here, the key value pairs that I've done are 1, 2, 3, etc. that map to each month in the year, and I've just gotten this started here. So let's run type on months to verify. Sure enough, the class association with this name is dictionary. Now we can fetch values for any keys in the list simply by typing the name of the name, and then using our square brackets, we can pass in directly key or value pair objects. I'm going to bring back 2 for our key value 2. That brings back February, of course. What if we put in a key that doesn't exist? Well, as expected, that would bring back an error message. The error here is that there's no element in this list, no key value pair where the key is 4. In my experience, the easiest way to add items to an already existing dictionary is to do something like this. Use the name of your dictionary, and then in your square brackets, add your next or your new key value. I'll just bring in 4, and we assign that to whatever value we want. We could use different data types, of course. I could just as well make month for an integer if I want to, but of course in this example that wouldn't make sense. When you see an unexpected traceback here, at least in my personal experience, it tends to be syntax more than anything else. I have to remember the dadgum name. It's as easy as that. So this is called adding to a dictionary by assignment. So we're adding the key value, the new key value in square brackets, and then we're using equals, our assignment operator, and then we're doing our value. So we could stretch this out all the way through the end of the year if we wanted to. Whereas I showed you earlier, we can just pass in a key value to return its associated value. We can also perform several other operations like, let's just see the list. Let's type months, dot, and then pause while idle gives us our method list. Why don't we start with the keys method? Keys comes back with the first part of those key value pairs. If we want to see the other side of the equation, we can run the values method to bring back just the values. If we want to modify this eminently mutable dictionary in place, that's certainly doable. Let's echo back the whole thing just so we can have it at our reference. Let's redefine key 4 as something else. Or how about we be very Pythonic and do this instead? Now, one thing that's significant among many with dictionaries is that this is an unordered sequence of values, okay? So that is to say, each time you run, in this case I'm echoing back my months dictionary, it happens to be giving back these in sequence, 1, 2, 3, 4, but it does not have to. Therefore, slicing is not allowed in dictionaries because the key value pairs don't have any intrinsic order or positional value. Because dictionaries are eminently mutable, we can make changes to their values in place. So why don't I try this? I'll bring in key 3, and we'll change it from March to spam. We'll then do some conversions here. I'll create a name called month to list, and we now have a list. Now that's significant, you'll note, because by default it grabbed only the key portion of those key value pairs. If we wanted to grab only the values, we know how to do that now, don't we? We could run the list to convert and then pass in months.values to drill into that dictionary and extract only the value portion of that dictionary. Remember, I mentioned that we can nest these different sequence types. That is to say, we might have a tuple that I'll just create right now. And so long as that tuple includes consistent immutable data, we can then add to our original months dictionary. Let's try an assignment here. We'll bring in position 4 and we'll add in tup. So now you see we have 1 January, 2 February, 3 spam, 4, and then an embedded tuple. I don't think I showed you how to embed lists actually. Embedding list on list is pretty easy. You see I've whipped up 2 list names here really quickly, L1 and L2. So if I wanted to add this L2 data to say the end of my L1, I could do an L1.append and simply bring in L2. That can be helpful for creating layers of complexity if needed in your Python code. To sweep up the shavings here, let me show you how to get a length count of a dictionary as well as how to remove an item. I created a dictionary here that maps similar, in fact it's not just similar, it's exactly to the example I gave in the whiteboard where we're mapping English words to Spanish ones called ADICT. We can certainly pass in this name to the length function. And notice that the length here with the dictionary refers to the number of key value pairs. That was different from our lists. You'll remember L1, if we pass in L1 to the length function, that gives us the discrete objects. And then finally, if we run len on a string object, it gives us the number of specific characters. All right, so let's bring back our dictionary again. Finally, the pop method is cool if you want to remove a specific key value pair from the list. So we can, in this case, do adict.pop and then simply pass in the key that we want to remove. And as we're scanning this list, we can see an example of what I talked about earlier, that a dictionary will never come back in the same order consistently. You see that we have 3, 2, and 1 presented this way, and when we first ran adict, when we first defined it actually, we defined it as 1, 2, 3. Interesting. So if we want to remove 2, or actually let's remove 3, we can simply pass in that key, and then when we run the name again, we now see just the 2. As usual, I'm going to complete this nugget by showing you a Python script that brings in most of what we've learned in this nugget, admittedly quite a bit. Remember, from idle we can use File, New Window to open up a new script file. I've created one called module4.py, and what this guy does is, let's take it a section at a time. The first thing we're doing here is creating 3 names, or 3 variables, that are going to bring back data from the user. I wanted to get first a string, then an integer, then a float. Now you notice that we're beginning to combine functions here, or stack functions. So val1, the prompt is going to be enter the string element 1 of 3. And we know already that once the user inputs that string value, it's going to come back and be bound to the string data type by default. Therefore, for our second prompt, where we want an integer, we're wrapping this input function in the int function. Pretty clever, huh? We can take 2 lines of code and combine them into 1. Similarly, for val3, we're going to ask for a float number, or a float element, and we're going to run the float function to make sure that val3 is in fact associated with the float data type. Now remember, we haven't yet gotten into debugging and exception handling. So right now, this procedural code is really fragile, because if someone were to put in, say, an integer for their string or a string for their integer, things could go very bad very quickly. This is just to get us gradually into the scheme of thinking Pythonically. Next, what we're doing is creating 3 other objects, lst, tpl, and dict, that are simply creating a list, a tuple, and a dictionary respectively, plugging in those 3 values that the user was asked to supply. So for our list, val1, val2, val3, tuple, and then for dictionary, I just arbitrarily added for my keys a string literal, first element, second element, and third element. I'm printing a new line here to give ourselves some physical space between code output. I'm doing that here in 2 spots. Remember, if you're not sure what a new line character is or an escape character, then you'll be definitely well suited for next nugget where we define those. Next section of the code, we're simply taking the input that we've massaged and echoing back the list, tuple, and dictionary, you see? So we're using the print function to give static string literal text back. Here is your list, comma, which is a space we know, and then bringing in the list, tuple, and dictionary. Add another new line to give ourselves some breathing room. Then we'll create a 4th variable called val4, where we're fetching a new string list element from the user, running the append method that's supported by lists to add what the user types in here to the list, and then we're echoing it back. Pretty straightforward. So let's go to run module. You'll notice also, let me pause here for a moment, that you can use the F5 key to run your code. And by default, you'll always be prompted to save your work before the modules run. That can get annoying sometimes, so to turn that behavior off, you can open up Options, Configure Idle, and then on the General page, Autosave Preferences, you can switch that from prompt to save to no prompt. That can make things faster. But certainly, I tend to use Control-S habitually anyway. Let's run the module. We're prompted for our string element. I'll put in spam, of course. Our integer element, we just have to put a straight ahead integer, so I'll just put 4,000. For our float, I'll add that float, hit enter. We get some new line space here. Here's your list, here's your tuple, here's your dictionary. Pretty straightforward stuff, right? Next step in this procedural program, what is your new string list element? Of course, that's going to have to be eggs. And then our final output, here is your new list, spam 4000, 3.232x. Data types part 2 of 2 review. Here we finished up our initial consideration of data types by investigating, comparing, and contrasting tuples, which were read-only, immutable, list-type objects, lists that, because they're so flexible, tend to be the go-to for a multi-element data type, and dictionaries, which can provide fast lookup, also mutable, and present data as key value pairs rather than individual items. As I've mentioned about 1,000 times before seemingly, we're going to be using these data types, as well as the string and integer and float data types from the previous nugget, all through the rest of this course. So if you're still feeling a little bit shaky about these, don't worry about it. By the time you're finished with this training, you'll be golden. I hope that this has been informative for you, and I'd like to thank you for viewing.